Section 1.1, Open Sets and the Definition of a Topology. Definition 1.1, let X be a set. A topology T on X is a collection of subsets of X, each called an open set, such that, number 1, the empty set and the entire set X are open sets. Number 2, the intersection of finitely many open sets is an open set. And number 3, the union of any collection of open sets is an open set. The set X, together with the topology T, is called a topological space. So to get used to this definition, let's try a problem from Munker's textbook entitled Topology. In this problem we have a set X, which is 3 elements, A, B, and C. And we have 2 different topologies on the set X, T1 and T2. And we're going to look for the smallest topology containing both T1 and T2, and the largest topology contained in both T1 and T2. Well, before we look for those topologies, let's try and illustrate T1 and T2. So, start with T1. We have 3 elements in our set X, A, B, and C. And now I'll represent the open sets in the topology by just sort of drawing regions in the plane. So that region will represent the empty set because none of the 3 elements A, B, or C is inside of it. And then we have a subset consisting just of A, another one consisting of A and B, and finally we have X, which consists of all 3 elements. And there's a picture of our topology. Now let's draw T2 as well. And it's a topology on the same set X, so we have the same 3 elements, A, B, and C. And the empty set is still an open set, as always, for a topology. And we also have the subset consisting just of A. This time, instead of A and B, we have B and C. So there's an open set, and finally X, which contains all 3 elements. Okay, so you can check that each of those satisfies these 3 properties of a topology, that the empty set and the full set are both open, the intersection of finitely many of them is open, and the union of any collection of them is open. Now we want to find the smallest topology that contains T1 and T2. Well, the first thing to think about would be, what's the smallest set that contains T1 and T2? And that would be the union of the 2 sets. So let's just compute the union of T1 and T2. And let's see, it would have to contain the empty set and X itself and A and AB. So far that looks just like T1. And then the only extra element that T2 contains is the subset BC. So that is the union. Now we have to ask ourselves, is that a topology? It certainly contains the empty set and X, but does it contain the intersection of any finite collection of subsets? By the way, the finite doesn't matter here because the set is finite to begin with. And, well, it doesn't, right? This, well, it's not a topology since it doesn't contain the intersection of A, B, and BC, right, which would be the set consisting just of B. So we need to add B to it. All right, so the smallest topology containing T1 and T2 is, let me copy what we had up here, and I'll just add in the subset with B. Now, we still need to check that that's a topology, right? Because now we have a new set that we could take the union of it with other open sets or the intersection, but if you check, we don't get anything new by doing that. So this is a topology. Okay. Well, now let's think about the largest topology contained in T1 and T2. So our first guess for that would be the largest set contained in T1 and T2, which would be the intersection of the two sets. So T1 intersect T2 consists of all elements in both. In particular, contains the empty set and X, and the set consisting just of A. And that's it. And if you think about that, it does contain the empty set in X, and it is closed under taking intersections and closed under taking unions. So it's a topology, and therefore it is the largest topology contained in both T1 and in T2. And that does it.